Development of atomic structure. So first in our study of atomic structure, we want to talk about the electron. And J.J. Thomson was the person who discovered electrons. He studied electrical discharges in a vacuum tube called cathode ray tubes. So let's look at what a cathode ray tube looks like. A cathode ray tube is a vacuum tube with a cathode and an anode end of our tube. And high voltage energy source is connected to this vacuum tube, and it produces a cathode ray. And since these cathode rays were attracted to the positive end of the magnetic field, it was determined that these cathode rays must be negatively charged and contain negatively charged particles called electrons. So when we look at electrons, they were determined that rays were made of negative particles that J.J. Thomson called electrons. Now when we look at the model of an atom, it was very different back in J.J. Thomson's time than it is today. J.J. Thomson determined that there were these negatively charged electrons in atoms, and it was known that atoms are electrically neutral. So there must be positive material in an atom that canceled out the negative charge on the electrons to give us atoms that are neutral. So J.J. Thomson developed what was called the plum pudding model for the way that the subatomic particles in an atom are arranged. So this plum pudding model looks something like this. J.J. Thomson postulated that atoms consist of a diffuse cloud of positive charge with electrons embedded randomly within it. And the negative charge and positive charge cancel out so that those atoms are electrically neutral. Millikan worked on the mass of an electron, and he used a charged oil drop experiment to determine what the mass of an electron is, and that was determined to be 9.11 times 10 to the minus 28 grams. Now we're up to the early 1900s, and we want to talk a little bit about Ernest Rutherford. What Ernest Rutherford did was test J.J. Thomson's model of the way that an atom is arranged, that plum pudding model. And what he did was he shot positively charged alpha particles at a gold foil. And he thought that if J.J. Thomson's model was correct, these large alpha particles would crash through the gold foil. But that's not what happened. When he carried out his gold foil experiment, some of the alpha particles did go straight through the gold foil, but some of the particles bounced right back to that alpha particle source. And what this did is it helped Ernest Rutherford define what we call the nuclear atom. So let's take a look at what Ernest Rutherford's lab looked like. Over on the left-hand side, we have an alpha particle generator. And over on the right-hand side, we have a thin piece of gold foil surrounded by a screen that can detect alpha particles. And what Ernest Rutherford expected to happen was when those alpha particles were shot into the gold foil, they would go straight through that gold foil and be registered on the back end of that screen detecting alpha particles. Some of the alpha particles did do that, but some of the alpha particles were deflected by the gold foil, and some were deflected by very large angles all the way back to the original source of the alpha particle generation. And what he determined is that the atom must be set up not as a plum pudding model, but the positive charge in that atom must be concentrated in the center of the atom, which causes some of those positively charged alpha particles to be deflected. So if we look here over on the right-hand side, we have J.J. Thomson's idea about the way that an atom is arranged, called the plum pudding model. We've got that positively charged cloud and the electrons embedded randomly within it. And if that were true, those alpha particles would pretty much go straight through the atoms. But on the right-hand side, we have the new idea about the way that atoms are arranged, determined by Ernest Rutherford, which shows that instead of having the positive charge spread uniformly throughout an atom, it's concentrated in the center of an atom, in a nucleus. And in this case, the alpha particles, some of them passed straight through the atom, but the ones that came close enough to be deflected by that positively charged nucleus bounced back on that detection. So when we talk about modern atomic structure, we're dealing with a tiny nucleus with a large cloud of electrons. The nucleus contains two types of subatomic particles: protons, which are positively charged subatomic particles, and neutrons, which are neutral subatomic particles but add to the mass of the atom. So if we were to look at a model of what our atom looks like, we've got the very dense center core of an atom, which we call a nucleus, and that's designated in blue in this picture. And then we've got outside the nucleus where the electrons are found, and that's designated with kind of the pink shade outside the nucleus. And when we look at the relative size of the nucleus to the atom, it shows that the nucleus is about 100,000 times smaller than the size of the overall atom.